All right, so welcome to lecture 20. Before we dive in, I just want to kind of review where we've been and where we're going. So lecture 17, we just thought about heat transferring from things that are hot to cold. So that's kind of this vicinity. We looked at how much energy would be transferred if you're going to raise the temperature, right? Raise the temperature of a substance that's a certain amount of mass by a certain number of degrees. If it's just a physical change you're talking about, Q equals MC delta T. Then in lecture 18, we started looking at changes in potential energy within a system. And we said potential energy is related to attractions. So anytime there's bond breaking and bond making, that's going to be accompanied by changes within potential energy. And anytime potential energy changes, kinetic energy changes to conserve energy. And that is why kinetic energy gets transferred either to the surroundings or from the surroundings. So lecture 18, 19, 20, we're all in this area, thinking about changes in potential energy and how do we quantify how much energy is getting transferred. Last time we met, we used bond energies, okay, to quantify how much energy is transferred in a particular reaction. So we drew Lewis structures, we figured out what bonds are breaking, what new bonds are forming, and we used these energies to figure out the total delta H of reaction, or heat of reaction, or enthalpy of reaction, okay? The heat of reaction is always kind of a measure of what is the potential energy difference between state 1 of a system and state 2 of a system. Any questions about that from the last lecture before we move on? Okay, so what we're gonna do today is I'm gonna teach you another way of quantifying the heat of reaction. Okay, so you're gonna start by comparing similarities and differences. So let me just take you to the top really quick. In this lecture, rather than bond energies, we're gonna use enthalpies of formation, and the whole lecture will be trying to figure out what does that mean. So how do we use enthalpies of formation to predict the heat associated with a reaction? In other words, delta H. So by the end of this lecture, what I want you to be able to do is use these enthalpy values that you would look up in tables to calculate delta H. And I need you to be able to draw energy diagrams to represent these reactions. These are what I mean by energy diagrams, showing potential energy of state 1 and 2. And then you need to learn how to write the reaction equation for the enthalpy of formation. So we're going to be learning how to do that as well. But big picture, I want us to start by just comparing the two methods for calculating heats of reaction. So both of these energy diagrams that you're looking at are for methane, CH4, combusting or reacting with oxygen to make CO2 and H2O gas. We don't know the heat of reaction, except both of these energy diagrams are there to calculate it. So these are bond energies. This is what you learned yesterday or last time we had a lecture. And this is the new information. Each of these are enthalpies of formation. So I'm gonna send you into breakout rooms, and in your rooms, what I'd like you to do is notice any similarities and differences between the two methods. And as you're noticing things, similarities and differences, you can kind of take some notes down here. I do wanna highlight one typo. This says CO2 solid in both cases, but I meant it to say CO2 gas, so there's no phase change. You could just kind of make a note, CO2 gas in both cases. Okay, any questions before I send you into a breakout room? All right, I'm gonna